Okay, hello. Last homework from this unit is from section 10.5 of the textbook, which is really like 3 sections in one. Gossett puts together, well, everything. The concept of a planar embedding, planarity, the proof that K33 and K5 are not planar, Kuratowski's theorem, not a proof, just an introduction. Then also all the introduction to the platonic solids, the fact that the graphs of the platonic solids are themselves planar, the concept of a stereographic projection, also known as a Schlegel diagram of a polyhedron down to the plane, Euler's polyhedron formula, a proof of that, a proof that there are only 5 platonic solids, the concept of coloring a map, duality, and finally proper coloring of a graph and chromatic number. All put into one big section, and now this is one big homework, which in our class was 2 different days homework. This was due the first day, and this was due the second day. So let's go. We're gonna go over it, and then that will be hopefully this will be the last video I make this year. Woo! So this is only like now a week old, so that's pretty good. And this one was due just a couple days ago. So I said to put them all together. Let's go over it now. What are we doing? First problem, show that the Peterson graph contains a subgraph that is homeomorphic to K33 and so is non-planar. Click and drag software is recommended. Thanks, Gossett. Here we go. Here's the Peterson graph. What are we trying to do? We're trying to show it's not planar. How can we do that? Kuratowski's theorem says it's not planar if there is a K33 or a K5 hiding inside of it. Specifically, Gossett says there's a K33 in there. So let's go. Do you see the K33? Okay, I pretty much don't. By the way, I didn't prepare any of it. I mean, I put a lot of effort into preparing all the materials, but I didn't actually think through any of the problems yet. So I don't know whether that will be good or bad. So if you're very smart, then you just see this maybe like immediately. And if you're me, you don't see it. So actually, this could get ugly. Let's see. All right. Yeah. Well, okay. Let's be smart. We have 10 vertices. And what does it say? Click and show a subgraph that is homeomorphic to K33. So first of all, there's a couple of ideas. We could maybe we don't need all of this. I bet. Here's the thing. I bet that I can't delete any vertices. For example, suppose I delete A. I bet that now this graph just is planar. As I'm saying that, I'm not so sure that it is planar, actually. Possibly wasting our time. Yeah, see, there we go. No. No, but there we go. No. So actually, it might still not be planar, even having deleted A. So perhaps it's worth it to maybe try. Okay, so what is K33, of course? K33 is a graph with 9 edges, and a bunch of vertices have degree 3. So there's a chance that I've just stumbled upon it just by blind luck. That would be sort of unlikely, right? So let's see. That connects to A, but nothing connects to D. No, but through G it does. All right, this is not like a reasonable systematic approach here. So, okay, I'm going to hit the refresh button because I don't want to delete that vertex A, I don't think. But anyway, I'm looking for a K33 subgraph. How do you do this? I think the answer is you just have to be smart. And so far, it's not looking good for me. But I guess armed with the idea that this graph is completely symmetrical, it shouldn't matter where I begin. So let me just begin. Let's put this up here. This also up here. And this also up here. That looks kind of promising, right? And then 1, 2, 3. All right, so I think that I just did it already. kind of by accident. So what I believe is, do I really believe this? Are you squinting and are you seeing K33 happening before your very eyes? I do. But here's what I believe needs to happen. Okay, maybe this is not K33 because this one is connected to here, but nothing is connecting it to... No, so it is through A, but then nothing is connecting it to I except through C? I was worried this might happen. Okay, give me another minute. I feel like I'm close, but also it's possible that that's just an illusion and I'm not close. The problem is I can't get from J to A and C both through B. So that is just kind of a problem, right? Because I need to either follow B to A or B to C. I really just want this to work though, so badly do I want this to work. Did I have H up here before? Come on, this has just got to be right, yeah? So I think now it's good? Yeah, because J, B, A, and D, C, H. Okay, so I don't know what I did, but I accidentally, let me just confirm everything before I start deleting stuff. Yeah, we're actually accidentally good. Okay, so now I'm going to do the following. I'm going to delete this edge IE, which is certainly allowed. And I'm going to delete BC. And I believe that I have now, this just straight up is K33. Or rather, it's not K33, but it is homeomorphic to K33. Because I have this edge from H to F. Here, let's like do some colors or something. I have this edge from H, well. So how do we know it's K33? Because if you're watching this far, maybe those three are blue and these three are like red or something. Oh yeah, watch. I remember how this goes. I'm gonna make this beautiful. Let these three be red, because that's kind of what it means to be bipartite, that the vertices are colorable. And also, I feel like they should be bigger. So, okay, at the risk of like wasting your time, let's do this. Boom, boom, boom. So those are those guys, and then no, and then here we shall also make this big, and then yeah. Okay, so that is my coloration. Is this really K33? Well, it's not actually K33. It's homeomorphic to K33. So now what I'm going to do is I'm going to take this dot and I'm going to make it like ridiculously tiny, and also like not even label it anymore. See that? This is a brilliant little move. And now it's just like, that's just is K33, man. So do you just like see it? You should. Those things are still kind of there, but technically this is not K33, but it is homeomorphic to K33. It's the K33 shape. Yeah, look at this. Look at this. Yeah. Woo! Success, we won. It only took like 10 minutes. Okay, good. One problem down. So my answer to this is just like check. Okay, I'm going to pause this, be back in 1 second. Okay, we're back. More problems. Let's go. Number 5. Prove that every proper subgraph of K5 is planar. Okay, we pretty much did this in class. So maybe I don't want to do this again, but maybe I do. Let's go over here and let me just draw K5. So 1, 2, 3, 4, 5, and it's K5, right? So it looks like this. Sorry, I could have prepped this in advance, but it's not going to take too long. Okay, and boom, 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 and a boom. Okay, so there's K5. Prove that every proper subgraph of K5 is planar. In other words, delete anything and it's suddenly planar. Well, okay, what might we do? We could delete a vertex. If I delete a vertex, certainly this is planar because, boom, that's just K4. Okay, so instead of deleting a vertex, let's delete an edge, even a single edge, any one. The graph's completely symmetric, so it doesn't matter which one we delete. So without loss of generality, delete that edge. Well, now suddenly this graph is planar. How do you know? You know, man. There it is. That's just a planar graph because I just showed it was planar. So, okay, check. Every proper subgraph of K33 is planar. Well, this is basically a K33. Maybe I don't want to do that, though. Maybe I want to make my own real K33. So, boom, boom, boom. And I'm just reusing the same file instead of opening a whole new one. This will only take a minute. Shump and shump, shump and shump. Okay, so this graph is not planar. We proved that, but if you delete just one edge and the graph's totally symmetrical, so it just shouldn't matter which one. Let's delete this edge. I claim that this is now planar. Why? Well, let's see. We can do something like that, and I just already win. There it is. Okay, so that was maybe worth doing. Check. Next. Is the following graph planar? Support your answer. This is the alien spaceship graph. Oh man, I practiced this, but I practiced this like a week ago. Okay, I did make this graph. This could get ugly, guys. So here we go. Alien spaceship graph. I did this live a bunch of years ago, and we just tried for 25 minutes and we got nowhere. But then I did it. Oh man, I did it over again, but it was a week ago, so of course I've forgotten. I think the answer is there's a K33 hiding in here somewhere. Where? Let's go. Let's go find it. No one's going to do this problem for me. All right, am I smart enough to just see it? I don't think so. I will note that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, I have 12 vertices. So some are just not going to get used. So, you know what? Here's what I think. Watch this. I am kind of vaguely remembering. Here's what I remember. I remember staring at this for a while and thinking, man, even without C, D, K, and L, I think that this graph is not planar. So here's what I did. I dragged C, D, K, and L far away. And watch this. I'm going to select all these objects. Let's see. Did that work? And let's make them like small or something. Okay, that didn't really do what I wanted it to do. Here, I'll just try it again. So let's make this like really tiny. So like almost invisible, but not quite invisible. And then I will do a little bit of this. So I want these to like go away, man. Go away. All you things that I think aren't important. Okay. And I think that even just without that stuff, I think what remains is just already not planar. And now I'm feeling a little bit better about this because what do I have? 1, 2, 3, 4, 5, 6, 7, 8. Uh-oh. 1, 2, 3, 4, 5, 6, 7, 8. So maybe it's not K33. Maybe it's K5 I will somehow find. But how am I gonna do that? Because wait a second, 1, 2, 3, 4, 5, 6, 7, 8. So no, I guess it is K33 because I have 8 vertices, but K33 has 6 vertices, and they all have degree 3. Okay, so let's just find the K33. This is pretty much exactly like what we did a little while ago. Maybe it's once again it's totally symmetrical, so it maybe doesn't matter, and I maybe just have a lot of choices. Actually. You would think that if you do a problem enough times, you might just get it, actually. But no, that can't work. So B's got to be down here, and I's got to be up here, and maybe G is down here. Did I just accidentally win? I think I did. I think I just accidentally won. Not accidentally. I really just like did math there. Okay, so good. What do we got? I found my K33. So in other words, here is why this original graph is not planar. It's not planar because it has a subgraph that's not planar. Certainly, if part of your graph is not planar, then the entire graph is not planar. So I'm going to show you that this subgraph is not planar by deleting a bunch of stuff. So these things, I'm now going to just delete them. So that stuff's just gone. Then I'm going to delete... oh, wait. I got a little bit too cocky because this doesn't quite work anymore, does it? I need... What's the problem? What do I need to do? Maybe it's H that needs to be... Sorry, I was almost there, and then I looked more carefully at what I was doing, and I realized that this doesn't work, or does it? J to I, J to A, J to F. So I can just delete EH entirely. Yeah, okay, so watch. Now I'll delete segment EH. Boom. So it's just straight up gone. So here I'm faced with a graph which is a subgraph of my original graph. And once again, I clearly just have not exactly K33, but something which is the exact same shape as K33. And okay, this is this is Kuratowski's theorem, right? Kuratowski's theorem says that every non-planar graph has a K33 or a K5 hiding in it. But actually, you don't even need Kuratowski's theorem to do what we need, what we're doing right now. Kuratowski's theorem just says that this method that we're pursuing is always going to work. But here, it's the simple fact that we have proven that K33 is not planar. And since K33 is not planar, neither is this graph, which is basically the exact same shape as K33. And so, let me just do that thing I did before. Maybe this is not necessary, but it's kind of like nice or something, which is make this really big. And so those are the blue dots of the bipartition. And these are the red dots of the bipartition. And then these points I will make like really tiny so that they're essentially like not even there. And boom. And now I hope you see that this is K33. Since K33 is not planar, then neither is this graph planar. And then neither is the big graph planar. All right, I feel like I've proven my point. I feel like I got this now. Let's do number 7. Is this graph planar? I hope the answer is like just yes. That would be a nice change of. That would be a nice change, but I actually have no idea. I didn't even really give you guys even a second to look at this. I just kind of started moving. But yeah, it felt like it was probably going to be planar. In fact, this is just an octahedron. It's just the octahedral graph. Every region has degree 3. Every vertex has degree 4. This graph's completely regular. That's an octahedron. Okay, good. You're just taking care of this homework. Alien spaceship graph. No, you are not planar. I found a subgraph of you, which is homeomorphic to K33. Is this graph planar? Yes. And I have just produced a planar embedding by dragging around. I think that I'm actually done now with what was the first half of the homework. So that was like a whole day's homework right there. 3, 5, 6, 7. Yep. And now we had a whole week went by or something. And this was the homework that was due just days ago. Look at me, all caught up. The question is, this is number 9, says, which is a 4-parter, what is the chromatic number of each of the following graphs and why? Give some supporting evidence. Okay, so this is a 2-part problem. This is the icosahedron graph. So we're just going to do this. I didn't make GeoGebra files for these because I think we're just doing the coloring, so we don't need to drag around really. So okay, let me just begin. I am going to color this vertex red. Okay, well, no other vertex connected with it can be red. So this vertex has to be a different color, so let it be green. without loss of generality. What can I say about this vertex? Well, it's connected to the green vertex and the red vertex, so it can't be green or red, so it's got to be yellow. Okay, now let's take. Now you have to be a little bit more strategic. What about this vertex? Could it be red? It could be red. Could this be yellow? It could be. Could this be green? It could be. But here we see. Okay, so what I want to do now is I want to sort of say, let's try to use the fewest number of colors. Let's try to see if the graph could be done in 3 colors. So if I'm trying to do it in 3 colors, then that has to be yellow because it can't be red or green. And if I'm trying to do it in 3 colors, then this vertex has to be green because it can't be red or yellow. But now we see a problem, right? Because this vertex can't be red, green, or yellow. And so no matter what, totally arbitrarily, if I try to, this is sort of just a proof, basically, that you can't color this graph in 3 colors. Because this vertex is arbitrary, then this one is an arbitrary new color, then this one has to be an arbitrary new color. What can I say about this vertex? Well, if you think it can be done in 3, then it has to be yellow, then this one has to be green, but then this one can't be red or yellow or green. Another way of looking at it is that this is kind of a K4 situation. So I think at least 4 colors are going to be possible. So let me color this blue. And now that I've shown, so what have I shown? What I've shown is that this graph, that chi of this graph has to be at least 4. In other words, chi is the minimum number of colors required to properly color this graph. And since I've shown it can't be done in 3, then what I've shown is that it requires at least 4. Okay, well now, let me just try to do it in 4. And if I succeed in doing it in 4, then I'm good. All right, so now what can I do? Well, I got to be a little bit smart again, maybe. Or do I? This one down here, I can't really say whether that should be red or blue. I have no idea what to do now. But anyway, I'm pretty sure this can be done in 4. So let me not give away my strategy because I don't have one. Let me just try to do something. So I'll just make this red, but I think green was also possible. No, I take it back. I do want it to be green because if that's green, then this can be red, and I need it to be red because it's adjacent to the green one. Well then, like this can be yellow, I guess. And then this one here can be blue. I actually don't know what I'm doing or whether this is gonna work. No, that just doesn't work. Okay, hold on. New idea. Let this be blue and this be... Oh yeah. Yeah, that'll be fine. And this will be red. Hold on. Wait a second. I guess this doesn't have to be yellow. This could be red also. Okay, we need to think a little bit here. This could be red. Does this solve anything? And then this is yellow. All right, so I don't actually even just know what happened, but I did it. That was wildly unsystematic. I crave some kind of deeper understanding. I guess every triangle, something, don't know. Maybe I don't care. All right, so good. Anyway, I win. In fact, and what do I mean by I win? I mean, hey, that the chi of this graph is in fact 4 exactly. Okay, 1 down, like 4 to go. I'm not sure we had to do all of these, but anyway, it's pretty fun. This is the Haywood graph. This is a famous graph. Hey, it's not obvious at all, but if my memory serves me correct, this graph is just straight up bipartite. Can that be true? It might be true. That's red. Color this yellow. So now color everything adjacent to it red. But then color everything adjacent to those yellow, and then color everything adjacent to those red. And okay, so that has to be yellow. This has to be yellow. Let me just finish this. This has to be yellow. This has to be yellow. And though not initially obvious at all, this graph is totally regular. Every vertex has degree 3, and this graph is indeed bipartite just by inspection. So in fact, the chi of this graph is 2. Because 2 colors are required, certainly, but can be done in 2. Okay, good. More. The Walther graph. All right, I really should have probably Googled this in advance. I have no idea what the chromatic number is. I mean, I just have actually no idea. No idea. Every vertex has degree, or no vertex has more than degree 3. I bet it's like 3. I guess I could try to color it in just 2 and see what happens. Okay, so we do red, yellow. I guess I could make these both red, and then make this yellow. But then this would have to be red, and this would have to be yellow. Wait, I'm gonna lose it if this is bipartite. Come on, no freaking way. No way, no way, no way, no way. No, in fact, no. Alright, so it seems that this graph is also bipartite. That was just not something I was expecting at all. But there it is. Boom, boom. Okay, wow. Was there something deep I should have thought about this? Let me see. I'm the teacher of this class. I guess there are no odd cycles. That's something that we potentially could have noticed. Here's a cycle, but its degree is 4. Here's a cycle of degree 6. Here's a cycle of degree 8. Here's a cycle of degree 1, 2, 3, 4, 5, 6, 6. Here's a cycle of degree 6. Here's a cycle of degree 6, and a cycle of degree 6. So that is in fact how I could have known in advance had I thought to check this, that this is a bipartite graph, because the graph is bipartite if and only if there are no odd cycles, and this graph is certainly planar. It's divided up into regions, so one reasonable thing to do is to just count all those regions and note that all of them have even degree. Alright, that was pretty exciting. Here, I definitely don't know what the answer is to this problem, like, definitely not. So let's go. Let me once again start arbitrarily. Oh boy. Well, if that's red, this has to be a different color. But then, could this be red? I don't see why not. But then, could this be yellow? I don't see why not. But then, could this be yellow? Yeah, maybe. So I'm trying to do it in 2, I guess. Could this be red? Okay. But now, okay, so what's going on here? We have a 4, 5, 6, 7, 8. Yeah, okay, so a cycle, in fact, this is about to come up on the next page. Let me just do that really fast. Here are some sort of easy questions that we maybe should have done in advance or something. So what is the chromatic number of the following graph? Support your answer. So if you give me the cycle, so let's do A first, the cycle graph. So what's the cycle graph? It's just this thing, okay? And now here's the thing, I guess that, so this graph has degree 2, right? And okay, common sense suggests that I should consider the even and odd case separately. And well, there we go, right? In the even case, an even cycle graph is just bipartite, like fact. And so the answer is the chromatic number of C, I'll just say like 2n, is 2. So the cycle graph with an even number of vertices is 2. But here, it's going to come up right now that if we take an arbitrary, okay, I'm using 5, but there's nothing special about 5, that now here, right, this vertex is adjacent to one that's red and also yellow. And so I need 3 colors for this. And so I claim that that was a pretty good proof that C, like 2n minus 1 is 3. All right, so that's a good piece of background knowledge, right? Cycle graphs require 2 or 3 colors depending on whether we're going an odd number or even number times around. All right, stars and wheels. Stars, I feel like, are kind of a little bit stupid. Unless I'm misremembering, you know, the star just kind of looks like that. So I think the number of the number in the star graph is totally irrelevant. In fact, every star graph is just bipartite. And if every star graph is bipartite, then the chromatic number of any star graph is in fact 2. So now let's do wheel. I'm panicking and I'm doing something like dumb here, but I don't think so, because I think that wheel graphs are just, you know, they're just cycles with a dot in the middle. So so yeah, I guess it's going to be the same thing, right? It's going to depend on whether the thing is even or odd. So now, because the vertex in the center is, because the vertex in the center is adjacent to every other vertex, then a whole additional color is going to be required. And so, if I've done this correctly, then yes, I can make all these different colors. I can color the outside with just 2 colors, but then the inside has to be like a new color. So that's going to always require 3. And then here, if I try to do this with, say, only 2 colors, well, now it doesn't work. So this needs to be a different color than red and yellow, this one right here. But then in the middle, it's going to have to be yet another color that's different from all of them, since that vertex is adjacent to all this. All right, so we had to do that problem anyway, so I just thought we could do it now. So chi of, like, what am I doing? W2n is 3, and chi of w, like 2n plus 1 is 4. Okay, I chose to do that because I started to already have this sort of thought now that well, so here you might think that going around this circle, I could have done this in just 2 colors. But that's just not true, because let's see, like if this is red, yellow, red, right? But then if I made this yellow, then this would have to be red, but then that's already like off, right? Because these two have to be connected. So it's something like, because opposite vertices get assigned the same color if you're trying to color an even cycle graph with just 2 colors. But here opposite vertices are connected. And so the answer is probably that this is not such a good way of doing this. Man, I don't even know. Well, the argument is kind of breaking down, but I guess I'm just going to try to do this in 4. But I'm losing the argument of why it can't be done. Let me try to do this more carefully. So let me try to really do this. I mean, if anyone's watching this video, you might as well get an education. So let's go. So second try. Then I'm really going to try to use only 2 colors. So this has to be yellow. Let's let that be 3. I'm gonna try hopefully get a contradiction, and then it can't be done in 3. I just think the answer is 4 at least. So okay, let this be yellow. Let this be red. Well, you want to use as few colors as possible, right? So then you kind of want to make this yellow. But now you want to make this red. Okay, so far so good. Actually, what can this be? Well, it can't be red or yellow, this next one. So it's got to be a new color. Okay, great. What could this one be? Could it be Well, it can't be red or green, so it would have to be yellow. This is on the assumption I'm trying to do this with 3 colors. I don't know. Maybe this will just work. What could this be? Well, it could be red. So let's make it red. What could this be? Well, it can't be red or yellow, so it has to be green. Now, could this be green? Yeah, it could. Could this could be red, this one over here could be yellow or green, so let's leave that alone. What now? This one down here could be yellow. Whoa. This one could be, uh-oh, now I have a problem. That seems crazy. That seems crazy, but I guess the chromatic number, it seems that this vertex down here kind of ruins everything. I'm not totally convinced though that I had to do that. For example, let's go all the way back. Let's make this, I want that to be yellow. So that could be green and that could be yellow? No, that can't be green because there's a green over here. Jeez. I don't really know how to do this problem. But I'm seeing now that this is the problematic vertex. Wait, hold on. Let's go back. Oh boy. Is this all necessary? Could I have gotten away? Alright, the only way I could get away with this being red, yellow, or green, of course, is if this red, yellow, or green were not red, yellow, or green, but like something else. So then 2 of these 3 would have to be the same. Is that possible for 2 of these 3 to be the same? It doesn't seem like it would be that hard, man, to make this. Gosh, I don't know. Alright, I'm going to give up because, you know, what am I going to do? So I really have no idea whether this is right or not. I don't have a lot of faith in my answer. But I think my claim here is that this is 4. But I would also not be shocked if this could be done in 3 and I just didn't notice it. Let me try one more time for a second to see if I can prove that it can't be done in 3. I suppose there's like algorithms for this and stuff, but anyway, I don't know what they are. Who knows? I don't know. I got nothing. I'm just wondering if like, so this could be, say, green, right? Does that help anything? If this is green? This one doesn't have to be yellow. If this is green, no, that doesn't help. But that is kind of interesting a little bit. That doesn't actually change anything. Could this be red? Just no. Could this be red? Oh, no, it can't be. Without making that yellow, without making that green. That can't be green. Yeah, I don't know. I don't know. I don't know. Okay, that was like kind of annoying and frustrating. Anyway, I want to push on, so I'm going to just push on. Now I've lost all my confidence. Let me just try to do this problem. Well, let this be red. It's nice to do this kind of thing live where people can talk and stuff. Well, okay, if it has to be red, then everything else has to be something other than red. So this would have to be, say, yellow. Could this be then red again? I don't see why not. Could this be then yellow? I don't see why not. Could this be red? Could this be... this can't be sort of red or yellow, though. Which is to say... that there's kind of a cycle of odd length going around this thing. Therefore, at least 3 colors are going to be required, because 3 colors are required to color an odd-numbered cycle graph, and this is like even more than that. All right, now can I just finish this from here, like by maybe making both of those green and making this red? It would have to be. Then this would have to be red too. But now I see this could be yellow. Oh man. And then this apparently has to be another color. I'm very not convinced that let's Google this one. It seems to have a name. Graph. What is that? Yeah. That came up. Graph. Graph. Chromatic number 4. Boom, look at that. So I'm not dumb. It really does require 4 colors, although it was not till the last color. So, okay, that's a good way to do your homework. Just Google it. This alien spaceship graph is like not really a graph, which is why we tried to Google it once and we couldn't. All right, so I really don't know whether this is 4 or it could be done in 3, but anyway, not by me, not right now. Let's push on. We did this one already. What do we have left? Only a couple problems. Number 11. Oh boy. The dean of a small college wants to increase enrollment in summer school. She has decided to offer classes during 3 time periods: morning, afternoon, and evening. Okay, this is getting intense. This is a great problem, but I haven't actually looked at it in a couple of years. Morning, afternoon, and evening. Students may enroll in 1 or 2 courses. She has found 10 professors who are willing to offer summer courses. Okay, so there are 10 professors, and students can take 1 or 2 classes. Okay. The dean has asked students to indicate the courses they are interested in so that she can decide which courses should be scheduled in the 3 time slots in order to maximize the number of students who will be able to enroll in 2 courses should they desire to do so. Okay, so yeah. So this is like a kind of a scheduling problem. And right. So we have 10 profs. Yeah. And 10 courses. One professor is teaching each course. So it really doesn't, the profs really doesn't matter. We just have 10 classes. And we can enroll, we can schedule those 10 classes in any of the various time slots, morning, afternoon, or evening. But of course, I guess the understanding is that this is going to be like every day, right? So these classes are going to meet, 5 days a week or something, either in the morning, the afternoon, or the evening. Therefore, you can take 2 classes. You can just take 1 class, of course. But if you want to take some, there are some students who want to take sort of 2 classes. But if a particular person wants to take precisely 2 courses and 2 courses only, I want to take 2 courses and only these 2. If it turns out that in the schedule they both get scheduled in the morning time slot, well then that sucks because you can't take 2 classes at the same time. So then that person would not be able to take those 2 classes. So what you want to do, essentially, this is just duh. If you want, when you're making the schedule, you'd like to, if there's a student who would like to take 2, who wants to take 2 courses. If there are 2 courses that one student would like to take them both, then you want to put them in different time slots. Okay. I think that makes sense. Right. Well, so what we have done is we have established a graph. And here is the meaning of this graph. This graph has 10 vertices. Each vertex represents a class. Each edge between 2 vertices encodes the relation between those 2 classes records a relation between those two classes. And the relation is there exists at least one student who wants to take both of those classes. In other words, we put an edge between two courses if there is some interest by someone in taking both of those classes. So what does it mean what does it mean if you're an edge between two vertices? It means that ideally these two classes would not be scheduled in the same time slot, because scheduling them in the same time slot means that someone can't take both of them and someone wants to. Okay, so where is this going? Here we have a graph, and now this becomes a graph coloring problem, right? Can you color the graph in such a way that adjacent vertices receive different colors? And in this case, the different colors indicate that they are going to be offered in different time slots. And if you can color this graph, and by the way, there are only 3 time slots, morning, afternoon, evening. And so now the question becomes, can you, is the chromatic number of this graph 3? If the chromatic number of this graph is 3, then a perfect coloring of this graph is an assignment to each of the 10 vertices of this graph of a color, and that color can represent a time slot. And now you have solved the problem, right? Because every single student can take every single class that they want to take. All right, so that I think this is like kind of great. And so the question is chi of g of this graph equal to 3? And vague memory, I haven't gone on this problem in like 5 years because we're always running out of time. But I think that the answer is like no. Yeah, because now there are follow-up questions where they're like, well, I guess not. Okay, so what we're now going to do is, since we've been so successful at this for the last half an hour, we're going to try to color this graph with just 3 colors, and I think we're going to fail. So let me be like smart or something. Let's let this be red, because this graph has 4. Yeah, am I already? Do I already? No. So let that be red. Okay, well then 1 has to be a different color. 10 could also be that same color, yellow, but it could also not be. Well, okay, watch this. 1, 2, 10, 8, 4 is a cycle of length 5. So just automatically, at least 3 colors are going to be needed. So I think it's pretty arbitrary to do at least that. But now we see there's a problem, because this can't be green or red, so it has to be yellow. But then this would have to be green. But then this would have to be red, this number 6. And now, what can I make 7 and 9? I can't make 9 red, of course. But no matter what I do, I'm stuck. Because if I make 9 yellow, then I don't have anything. Oh no. Haha. Good thing my memory is bad. The answer is I'm done. So never mind. I did just properly color this graph. That's a proper coloring. So okay, congratulations. We did it. I should probably have read part B a little bit better, because I now see it's coming back to me now. The answer to this part A is it possible to schedule the courses so that there are no student time conflicts? Yes! And the answer is this is the answer, right? Let's, without lots of, it's irrelevant. So I don't know why I rewrote this. Let the morning classes 1, 3, 9, and 10 be offered in the morning. Let in the afternoon offer classes 2, 6, 7, and 8, and in the evening offer classes 4 and 5. And now every student is going to get to sign up for every single class, because amongst this group of 10 courses, there are none of these numbers are adjacent to each other, which is to say, none of these courses that are in the same time slot have the property that there's a student that wants to take both of them. Okay, that was very satisfying, very fun, feels like a real thing that I did. Hold on one second. I'm just gonna turn this off. Okay, pushing on. Is it possible to eliminate the morning session without causing any time conflicts? If it is possible, show us. Okay, so I think now the answer is just going to be no. And my reason is that chi of g is definitely 3. And in other words, if I try, what are they asking by saying, can you eliminate the morning time session? They're basically saying, like, can you get away with having just classes in the afternoon and evening? Well, you can do that, but not without conflict, because there will definitely be a student who, if you only have 2 time slots, who wants to take 2 classes that are in the same time slot. That's because this same graph, which still applies, can't be colored with just 2 colors. I think we argued that we totally argued that convincingly, because a subgraph of this graph is C5, and C5 is a graph that requires 3 colors. So since I can't color this graph in just 2 colors, then the answer to this thing is no. All right, we're just moving right along here. It's possible that everything I've done so far is right even. All right, this is fun. Find the dual of the following graphs. Show the superimposition. Blah, blah, blah. Okay, let's go. How do we do duality? We put a vertex at the center of every region, including the outside region, and then you connect 2 regions if they share a border. And so what you have now is something that looks like this. Have I crossed through every single edge in this graph? I think I have. This graph has 6 edges. It's just K4, in fact. And this dual graph also has 6 edges. In fact, this graph in part A is just the tetrahedron. And in fact, the dual of the tetrahedron is the tetrahedron. The tetrahedron is self-dual. This is a graph whose dual is isomorphic to itself. So that's pretty amazing. You can just confirm that what we now have is a graph with 4 vertices and 3 edges. So that's very exciting. Okay, good. B. This is getting tricky because, how do I do this again? Okay, so there's a vertex of degree 0. Okay, so I gotta like focus. There are 2 regions. That's just true. This is a region, and then there's an outside region. This vertex is degree 4. Let's just begin. That's a loop. That's a loop. This is a thing. And could that just be it? Gotta think for a second. Every region of which there are 2 becomes a vertex. This graph has 3 edges, so the dual graph now has 3 edges. Edges are preserved under duality. So original graph 3 edges, dual graph 3 edges. Every vertex of degree 1, like this one, is now enclosed within a region of degree 1 because there's 1 bounding edge. This was a vertex of degree 1, it's enclosed within a region of degree 1. This was a vertex, this was a region of degree 1, and now has a vertex of degree 1 in there. So I think it's just all good. And this vertex has degree 4, but it is now contained inside a region of degree 4 because it's in the exterior, and the exterior has degree 4 because like 1, 2, 3, 4. So I think that's just right. And here he says redraw it, so it's just going to be some kind of like, you know, jump type thing. All right, great. C. Yeah. Okay, let's go. 1, 2, 3, 4. Shump, 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 shump. And of course, there's an outside region. So we see that there's something like this going on. And zoom. And am I just like done now? Yeah, 5 regions, 5 vertices. Every edge has just been crossed. This vertex has degree 3, region has degree 3, vertex has degree region. The outside region had degree 4. Yeah, that's just it. That's just not that exciting. This was just, no, it's not K4. I don't know what that is. I'm done. All right, what's left? A couple more. This is a fascinating problem. It's not hard, but it is very interesting. Show that the graphs G and H in the following diagram are isomorphic, but their dual graphs are not isomorphic. So first of all, is that obvious that these two graphs are isomorphic? I suppose that it's not obvious, but it's also pretty damn clear that that is true, right? Because, okay, here, let's do this. Let's make this kind of small or something and stick it off in the corner. Of course, these are isomorphic because, just move it in your mind or whatever, man. This E is matched with Y, and F is matched with X, and D is matched with Z. And basically you just grab that E point, yeah, and then B is matched with V, C is matched with W, etc. Because now you just grab that point E and just drag it out. It's probably better if I did this with GeoGebra, but I don't feel like it, because if you just grab that point D and just pull it out and pinch F and D inside a little bit, you can just see that these two graphs just are isomorphic. Anyway, there it is. I just produced an isomorphism. Essentially, I just produced an isomorphism by matching C to B to V, C to W, E to Y, F to X, and D to Z. You can confirm that that's an isomorphism by just showing that every pair of well, okay, we're done. All right, so what's fascinating, however, even though these two graphs are isomorphic, these two planar and this graph is planar because this is a planar embedding. This is also a planar embedding. So this is a graph which is planar, which possesses two different planar embeddings. And so these are just two totally different planar embeddings of the same graph. Okay. The same as in the two graphs are isomorphic. However, so are these planar embeddings really different? They really are different because, and I can sort of see this already, right? This region has degree 3, degree 3, degree 3, degree 3, degree 3, and this outside region has degree 5. But here we have a region of degree 4. There's just no region of degree 4 here. But here there is a region of degree 4. So already I can see that when I produce the dual graphs, which I will do right now, the dual graphs are going to be not isomorphic because the vertex associated with this region here of degree 4 is going to have degree 4. But there's not going to be a vertex of degree 4 here. Okay, so this is kind of incredible. So let's just do it now. So here's the outside region, and so it's going to be oops, kind of like missed there. Oh man, cha 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 sha, and then sha, and then let's see. This connects to the outside, and that connects to the outside, and that connects to the outside. So, like I said, the outer region had degree 5, so that vertex is degree 5, 3, 3, 3, 3, 3. So this is all just looking great, and this is just all correct and stuff and good. Okay, now let me make the dual of this graph. Well, once again, I'll put a vertex on the outside. I got a dot, dot, and a dot here, so we get a little jump, 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 and then we go outside. These two are connected as well. This has degree 3, so jump, And what else am I doing? Like this, and I guess like that. So this outer region had degree 4. This vertex has degree 4. This region, like I said, is degree 4. This vertex has degree 4. Degree 3, degree 3, degree 3, degree 3. So, yeah, and I've already kind of said it, right? The reason why these two graphs are not isomorphic is that this one has a vertex of degree 4, and this one doesn't. All right, so that's kind of incredible. What it means is that duality is really kind of more of a geometric concept than it is a graph theoretic concept, right? That the dual of a graph really does depend on the particular embedding. It encodes something more. The sort of, with a graph that's planar, the partition of the plane up into regions in a particular planar embedding is something over and above the information, the discrete information contained in just the listing of the vertices and the edges, and you know, which vertices are incident with which edges. Somehow the planar embedding is something else. It's really a geometric kind of object. Okay, last problem. This is quite hard, but I think I know how to do it because it's exactly like what I did in class. I did it in the video 2 weeks ago, and then I also did it live in class on, I guess, last Friday. So here we go. Let G be a planar simple graph with n vertices and epsilon edges if every region has at least degree 4. Okay. So if every region has at least 4 bounding edges. So now just kind of like imagine a world in which no triangles are allowed, right? So imagine you have some, I don't know, some polyhedron or something in which every region has degree 4 or more. Then if this is a planar graph, planar, simple, it doesn't even say connected, but maybe that doesn't matter. I bet that kind of like matters. Let G be a planar simple graph with n vertices and epsilon edges if every region has at least degree 4. I hope they're not trying to mess with me. I hope, yikes. I hope it is to be understood that the graph is connected. Because only if the graph is connected may I apply. Only if the graph is connected may I apply Euler's formula, and that is going to be the key to the proof. So let's just hold off on that for a moment. Let's just assume that Gossip was sloppy and meant to say connected. Let's just do the proof. So all right, what can I say? Well, I can say let this graph G have let G have row regions, epsilon edges, and n vertices. Okay, great. And now what? Well, the degree of every region is greater than or equal to 4. Well, if that's true, then the sums of the degrees of all the regions has to be greater than or equal to 4 times the number of regions, because I'm adding up a number which is 4 or bigger row times. If every region has degree 4, then the sum of all the regions, the sum of the degrees of all the regions has to be greater than or equal to 4 row. But okay, but also when you sum the degrees of all the regions, you're actually counting for every region all of the edges which bound that region. But you do that for every region, and every edge is part of 2 regions. Or you have this kind of weird case where you have an edge which juts out into the center of a region, but still it gets counted twice because we basically like force handshake to be true by defining the degree of a region with an edge sticking out into it like this. To count that twice, which is to say the degree of this outer region in this graph that I've just shown you would be 6 in a kind of a way. I think this is the way that makes sense. You sort of start at a point and kind of walk along until you get back to that point again. How many edges do you cross? Answer 6 here. So okay, the point is that the handshake holds here, right? That the sum of the degrees of all the regions is, in fact, twice the number of edges. And therefore, dividing both sides by 4, I get that rho is less than or equal to epsilon over 2. And now I say, by Euler's formula, which I hope I'm allowed to use here, then the number of vertices plus the number of regions minus the number of edges, has to be equal to 2 exactly. And if that's the case, then, okay, what does that mean? That means that rho is epsilon minus n plus 2. But if rho is to be less than or equal to epsilon over 2, then that means that epsilon minus n plus 2 has to be less than or equal to 1/2 epsilon. And if I just subtract epsilon, then I get 1/2 epsilon plus 2 is less than or equal to n. What am I trying to show? So anyway, so 1/2 epsilon is less than or equal to n minus 2. That should say 1/2 epsilon. And finally, multiplying by 2 gives me that epsilon is less than 2n minus 4. Okay, so I did this problem. This is how it was intended to be done. And this makes me believe that the problem was designed in order to insist that this graph be connected. Is that actually true? Could I show an example of a disconnected graph maybe which violates this formula? I bet not, because, geez. I guess it would have to be something like this or whatever. But now, I mean, it just is true. Here we have 8. So we just have well less than. So there's a tiny chance that Gossett wrote this problem intentionally like this, but I don't know. That would seem maybe too hard to me, because if you can't use Euler's formula, then I don't know how you're going to do this problem. And in fact, if your graph is disconnected, then there is a theorem that says that this is not 2, but in fact it's even more than 2 or something like that. I'll stop there. All right. I think I did this homework pretty well. There is a chance that there is an error. This one problem I'm still not sure of myself on. I think there's actually a video of me somewhere on the internet solving this problem where some smart kid did it. So I probably should have watched that video first. But I bet this is right, but it could be wrong. But otherwise, I'm pretty confident of my answers here. Typical video, medium quality, not particularly efficient. Hope you watch it on 2x speed. Goodbye. Hope you enjoyed this class. Later.